theory now. So what we're going to try to develop now, we kind of had this model of electron transfer to interface, right? But it was sort of, we drew some curves, and we said, okay, there's probably a potential energy surface, right? We drew these curves, and we said O plus an electron and R, and we talked about how we can shift these curves up and down. But we didn't really have a good molecular picture of it, right? We kind of just said these curves probably exist. There's some pathway. The electron transfer occurs over, and we can tune the energy of the electron by applying a potential. But we don't really have a good molecular picture. And so Marcus theory is going to give us a good microscopic molecular picture of electron transfer. Microscopic picture of electron transfer. This is Marcus theory. So this is done by Rudy Marcus, and what we want to do is connect molecular structure and environment, like the solvent, to electron transfer rates. So let's consider two different types of processes. We'll call one an outer sphere process, and that's what we've been talking about so far, outer sphere electron transfer. And I'm going to give you a homogeneous molecular picture. So imagine two molecules that you have an O and an R, and they can exchange electrons, okay? An electron can hop from O to R, or from R to O, sorry. And here's a specific example that Bard gives: cobalt hexamine, 3+ plus chromium, tris bipyridine, 2+ goes to cobalt hexamine, 2+ plus chromium, bipyridine, tris bipyridine, 3+. Okay, so this is a electron transfer reaction, right? Because I'm going from 3+ to 2+. So what's getting reduced? The cobalt complex.
How many amines do we have going on here?
We have. How about that? So hexamine. So which one's getting reduced? Cobalt or chromium? Cobalt, right? Cobalt's getting reduced. So chromium is the reducing agent, and cobalt is the oxidant, right? Oxidizing agent, or the oxidant. Okay, so this is an outer sphere process, because basically you can think about these are very tightly bound ligands that can bump into each other, exchange the electron, and float away, right? Like two hard spheres hitting each other, two pool balls hitting each other, exchanging the electron and bouncing away from each other. That's outer sphere, okay? That make sense?
Yes.
There's no exchange of ligands during this process. But another example that's inner sphere, then this is actually, inner sphere is much more relevant for catalysis and things like that. Okay, inner sphere, you might have cobalt pentamine chloride, 2+ plus hexaquachromium plus going to a complex where you have NH3 cobalt bridged by a chlorine, CrH2O 5, and the whole complex with a 4+ charge. So we've actually lost the water plus water. Yep. Good. So we've done an electron transfer, but now it's happened via a complex where there's actually chemical bonds or exchange of ligands between the two species. So the cobalt and the chromium are now bridged by this chloro species. So there's actually a chemical change that accommodates the electron transfer. Okay, so this is homogeneous. What does homogeneous mean? Same phase. So this is typically, we talk about homogeneous, we mean in the liquid phase. And then we'll talk about heterogeneous electron transfer. We can use the same sort of nomenclature and have an outer sphere. So we have our electrode, electrode here. It's the electrode. And I might have a layer of strongly absorbed solvent and ions, absorbed solvent, ions, etc. And my reactant molecule, say metal, with some ligands on it, will never get inside this strongly absorbed solvent layer, and I can have an electron transfer from my electrode to the metal. That would be outer sphere. So this, we're changing the number of electrons on the metal in this case. The electron could also go on the ligand. That would be also, it could be an outer sphere electron transfer. But we're not changing the bonding between the electrode and the metal, right? So this is outer sphere. And then inner sphere, as you might imagine, is a situation where you have your electrode, and in order to do the electron transfer, we take our metal, and it might actually form a chemical bond with the electrode to enable the electron transfer. This is catalysis, electrocatalysis, because this bond, how this metal or how this species more generally bonds to the surface will determine how fast that electron transfer can take place. But many of the outer sphere redox couples we use are fast, like ferrocene-ferrocenium, for example, is a classic one. But they don't depend on the nature of the electrode, particularly. This one depends very strongly on the nature of the electrode because this metal electrode or species electrode bond strength can be dramatically changed by the chemistry of the electrode surface. Okay, so that's our definitions. This is heterogeneous, sorry. Heterogeneous. Electron transfer. So consider this. O plus R prime goes to R plus O prime. So this is electron exchange reaction. Right? So this is an electron exchange reaction. It's a homogeneous reaction, right? There's no electrons involved, electrons and electrodes involved. And one thing to remember, this is very important for Marcus theory, is electron transfer reaction are radiationless. No loss or gain of energy, no emission or absorption of a photon, right? Okay, so they're radiationless. So this requires isoenergetic electron transfer. Okay, so this is sort of number one, the first really important key concept. We talked about that a little bit in the context of Butler-Ulmer, right? And the other key concept is that reactants and products do not change configuration on time scale of electron transfer. Electronic motion is much faster than nuclear motion. So there's actually a very famous principle called the there's a Born-Oppenheimer approximation, and this is called the Frank-Condon principle. So if you remember that from physical chemistry, also the Born-Oppenheimer approximation is related. So electrons are much faster than nuclei. That makes sense, right? Electrons are teeny compared to nuclei. They have, many, many orders of magnitude less mass, so they can move very fast compared to the rate of nuclear motion. So electron transfer happens faster than a single vibration of a bond. Our goal then is obtain expression for delta G double dagger, so the free energy of activation, as function of parameters we can estimate or calculate. And I should say molecular parameters, right? Because then we could have a molecule, we could estimate the rate constant for electron transfer in this theory. Oh, and I should also say that we are going to consider outer sphere electron transfer in Marcus theory. So we're going to take now a similar approach as we used in Butler-Volmer derivation. So I'm going to draw a reaction coordinate diagram. I'm going to label this Q, and this Q is going to be some feature of system O plus R. Okay, so we'll get to what that is in a second, but sort of some measurable feature of O plus R, and it's actually going to be related to the bond lengths in the complex we're going to consider. So imagine I have, so there's the free energy of the system is going to depend on Q. And I can have a curve, just like before, for O plus an electron. And now I'm going to draw this curve with a very specific formulation. It's going to be a parabola. It's a parabola because it's representing actually a harmonic oscillator, ball on a spring, that's a physical model for two nuclei bonded together in the vibrational mode of two atoms, right? So if you have two atoms bonded, they're vibrating, and we can plot the energy of the system as some function of the difference between the equilibrium position and some other Q position between the two atoms. So if we stretch a spring, it increases the energy of the system, right? So that's all we're doing. And then we can write another parabola that's going to have a different 0 point, QR, and it might have a different minima value. I can draw a parabola there. And this is going to be R, my R parabola. So it's very similar to what we did for Butler-Volmer theory, except now we have specific shapes to these free energy wells. And these shapes are governed by harmonic oscillators, so ball on a spring. Okay, and then I can define what here is delta G for the reaction. And is it positive or negative in this case? Positive, right? Because that's delta G. And we'll call it delta G naught. Because just for simplicity, this is actually going to be the standard. We're going to take a standard reference state, so we'll call that the standard free energy. And then this is delta G naught, right? F E minus E naught for heterogeneous electron transfer. Because under standard conditions, if E equals E naught, delta G equals 0. Under standard conditions, right? Okay. So this is heterogeneous, it's homogeneous, but the same theory applies. And then we're also going to define a free energy of activation for the forward process. So what's the free energy of activation for the forward process? Can somebody tell me, we're on the graph, how I would label that? For the minima of O plus an electron, from here to where? To the crossing point. Okay. So this is delta G double dagger, and I think we'll call that forward in this case. And I could label the reverse process as well. Okay, so but now we want to actually write these expressions out in their functional form. So G O, G naught O as a function of Q. This parabola, right? Here I can use the same color. This parabola is given by K over 2 Q minus Q naught squared. K is a force constant for spring, which we're using to model the energy of our vibrating bond, okay? Or vibrating molecule. So where does this come from? Well, what's the, do you guys remember the restoring force on a spring? Kx, and it's actually like x minus x0, right? If x0 is the equilibrium position, right? So I could take that, kx, and if I take the integral of f dx, right? I just get kx squared over 2. And that's this. That's exactly this. how you do it. If you want to know the energy of a system, you integrate the force over position, right, to get the energy. And that gives you this expression. So that's all this is. Energy for a spring that's displaced from its equilibrium position. And I can displace it this way, I can also compress it, right? I can pull it out or push it in. And both ways increase the energy of that spring. Okay, and so now how do I write the other one? So somebody tell me what the other one is. K over 2. Okay, we'll assume it's the same spring, because it's the same molecule, it just has a different number of electrons on it, right? So it's the same molecule, it just might be a different, different 0 point. So the same spring constant, that's an assumption. And then what?
Q minus QR.
QR squared. Okay, is there anything else we need to account for to describe this parabola compared to this one? Because this one's higher by delta G naught than that one. Okay, so I have two parabolas. And the way to think about this, conceptually, is imagine I have, O, which is, say, ruthenium 3 plus, okay? Ruthenium 3 plus, and then I have R, which is ruthenium 2 plus, and it has some ligands around it. Which one's going to hold the ligands tighter? Why?
Smaller, it has a higher charge.
Okay, so more simple picture is more electrostatic interaction with the negatively charged electron donors on the ligands. It's going to pull those ligands closer. They're going to be closer together, right? So, I could put some ligands here. Okay, so these are ligands. And then I could, over here, I have ruthenium with the ligands further apart, right? Okay, should have drawn those different colors, whatever. And the point here is in order to jump from this free energy curve to this free energy curve, or the other way around, the molecule has to adopt a geometry where they both have the same molecular structure, right? So this one has to be compressed from its equilibrium geometry to look more like this one, and this one has to be expanded from its equilibrium geometry to look more like this one, and it's only at that point where you can have isoenergetic electron transfer. Only at that point. So that's all Marcus theory is. That's like basically it. And you can make a lot of predictions from it. So we'll keep going. There's a lot more to go through. But that's the core of it. And again, remember, these are not rate constants.
So the ligands don't reconfigure around the metal, they just
The bond lengths change.
the bond length themselves change.
Yeah. I mean, if you think about it, you want to transfer, the electron can only transfer when O and R have the same energy. So that can only happen when the bonds are stretched a little bit or compressed a little bit. And of course, what's doing the stretching or compressing? What's doing it? Why do they stress or compress? Why don't they just sit down here? Thermal energy, exactly. Thermal energy. Everything's vibrating, right? If you go to 0 temperature, no electron transfer. We know at Q equals Q double dagger, we know that GO naught equals GR naught. That's the crossing point. That's by definition, right? And so you can solve this for Q double dagger by just setting these two expressions equal to each other, right? At this point. So put Q double dagger in here and set this equal to this, right? And we can solve Q double dagger equals QR plus QO over 2 plus delta G naught over K QR minus QO. So this is the coordinate, the reaction coordinate number, in this case the physical significance, it's a bond length, where the electron transfer happens. Right? And it's related to this delta G naught, and it's related to sort of the difference between the center points of the two O and R species. Is we can now write delta G of the forward reaction, right? Forward reaction is just going to be equal to delta G naught of O at Q double dagger, right? Because we basically, I didn't tell you this, but we set this equal to 0 just as our reference state, right? So this distance, right, is just that, right? And that's just equal to k over 2 q double dagger minus q naught squared. That's just this term, right? You guys see that? So I'm just writing free energy at that point. And that's going to be my double dagger there, sorry. And now I can substitute in q double dagger, which we calculated just based on where these two parabolas cross. And so this equals k over 2 qr plus qo over 2 minus qo plus delta g naught over k qr plus qo squared. So I can expand this minus 2 delta g naught. I think we're just factoring out a term here. qr plus qo squared. qr minus qo over 2. So what we basically did is we combined these two terms to make this term, multiplied by 1 on both these terms to get a common denominator, so we could combine them to get qr minus qo. Okay, there's the minus qo, and then there's the bottom term, and then we're going to have a qr up here once we're filled them out. Okay, and then we can rewrite this one more time. I should just give you the final answer. qr minus qo squared over 4 times 2. So I do it in a second, times 1 plus 2 delta g naught over k qr minus qo squared. So what we did is we factored out the qr minus qo squared. I made a mistake here. This is negative. And then we're factoring out this term. That's all we're doing is factoring out that term, bring it to the front, and then we have 2 squared times 2, so that's 4 times 2. Okay, this is the actual equation that is the result of Marcus theory. And then what we do is we define this term lambda equals k over 2 qr minus qo squared. And this is called, here's a lot, the reorganization energy. Okay, so this is the reorganization energy. And notice this does not depend on anything to do about the size of the barrier, right? It has to do with how different are the products and reactants. How different are their equilibrium reaction coordinates or bond lengths in this case, and what the spring constant is for stretching them. So this is sort of like the difference in energy of the system, which is a spring, models a spring, when you move from this position to this position, right? So that's the sort of delta x, and that's the spring constant. So the reorganization energy is kind of like how much energy does it take to reorganize the system going from O to R. And it's a measure, it's an indication of how big this barrier ends up being. Or it affects the free energy of activation, right? Okay, so we can rewrite this. Delta G of activation equals lambda over 4. 1 plus delta G naught over lambda squared. So it gets very simple now, after all that work. The actual expression is very simple. And what's nice about this is lambda is related to molecular properties, right? You can in principle calculate these things based on simple theories of molecular properties. And delta G naught is thermodynamic, right? So it gives you a way to predict how fast what the activation barrier is for a reaction based on things you can actually calculate. Lambda physically represents energy needed to transform nuclear coordinates. Notice I don't just say one bond, it might be 6 bonds at once moving, right? It might be a rearrangement of the whole molecule. We'll find out it actually involves a solvent around it too, right? If the bond lengths are changing, the solvents have to rearrange too. So lambda actually has a solvent component, but it represents the energy needed to transform the nuclear coordinates of reactants to those of products. And we mentioned this analogy to a spring. We can write this for heterogeneous electron transfer the same way. F naught over lambda squared. So I can write it for delta G naught for a homogeneous chemical reaction or for an electrode reaction. Yes, solvent reactants, also electrostatic work that might need to be done if you have to move ion pairing, for example. So there's a lot of things that go into lambda, which we won't have time to talk about. So lambda can be further broken into an inner plus an outer component. So this is outer solvent, for example, and inner bond lengths, for example. So lambda inner can be calculated as the sum of all the normal vibrational modes of a molecule. So this is basically every single vibrational mode of the molecule, right? Every single way it can vibrate can be, its energy of all those vibrations can be represented this way. We just sum all those up going from the O to R, right? From the product to the reactant. So that's nothing more than we wrote before, except summing up over now every vibrational mode of the molecule that's relevant to the electron transfer. And you can calculate that with like density functional theory. And then lambda O is often calculated assuming solvent is dielectric media. So what does that mean? That means that like it doesn't have any, solvent doesn't have dipoles that can move around. It's just a uniform continuous media with some dielectric constant, like water has a dielectric constant of 80, right? So you can model water that way. It's not a very good model for water. It's a better model for nonpolar solvents, but it's one way you could do that. And so basically you can look in the book, there's an expression that says how you can calculate or estimate that based on the dielectric constant of the solvent. We're going to look at a prediction from Marcus theory. So alpha is the symmetry factor, right? From Butler-Volmer. But now because we know the shapes of these curves and how they cross explicitly, we can estimate alpha. We can actually estimate alpha. So alpha is going to be 1 over F dGF double dagger dE. So what that's saying is if I change E, what fraction of that changes barrier? So if alpha equals 0.5, right, if I change E, the barrier gets bigger or smaller by half of the amount that I change the electrode potential because of how those curves cross, right? So this is actually a definition of alpha in a more mathematical way, and I can calculate this. I can calculate this directly from Marcus theory, 1 minus F dGE lambda over 4, 1 plus F D minus E naught squared over lambda. And I can use the chain rule. I won't go through that, but the answer, so the function equals F E minus E naught over 2 lambda. So that's what alpha. So now alpha basically is telling you that it depends, it's about 1/2, but it depends also on lambda which is sort of how the curve, which is kind of telling you how far away those curves are, right? And the potential. So alpha can actually be potential dependent. And that kind of makes sense, right? If these are perfectly straight lines, and you're moving them up and down, then they'll always cross the exact same way. And that's, then you can get alpha is purely 0.5. But if these lines have curvature in them, right, how high they are will change the way they cross. So it's pretty simple geometric stuff, but it gets confusing when you layer it all on top of each other. So the model here, this would go into my rate expression in the exact same way, right? I can write a rate expression. The rate constant, K electron transfer, is proportional to e to the negative delta GF over RT, right? So the same sort of thing that we did in Butler-Volmer, except now we have something a little bit more